Okay, so what is a k-fold cross-validation? It is actually the most common method of cross-validation that is used in practice, and it's basically a refined version of leave one out cross-validation, only it is much more computationally effective. It's very simple, really. So if we have a data set, so I'm going to draw it like a long box. So we are going to split it into k groups of folds. So let's say, for the sake of this example, I'm going to use 4 folds. And then we are going to train. If k is 4, then I'm going to train 4 versions of our model. Right? So it goes like this. So in the first run, I'm going to take my data set. I'm going to remove this first fold, and I'm going to use this to train my model. And then this is going to be my f hat, say -1, and then I'm going to apply this to find the error on the fold that has been removed. So then I'm going to remove the second fold. So I'm going to use these and these together to form a new sort of like pseudo training set, and I'm going to train the second version of my model, so f hat -2, and then I'm going to apply it to those observations that were removed that it hasn't seen, and so on. So then I'm going to remove the third and the fourth. So this is how it goes. Then every time I train this model with one of the defaults being removed, I'm going to apply this model to the fold that was removed and find the mean squared error on the fold that was removed. Right. So this is mean squared error ith is where we apply this model. So that I called so f hat -I. So this is the model trained on the set with the ith fold being removed. So I'm going to apply it to x, say j, and this is going to be my y hat j with a sub index -I to indicate that the ith fold was removed. And then I'm going to find the mean squared error, so which means that I need to divide by the number of observations in that fold, and then I'm going to just find the mean of all these errors. Okay. Well, to be honest, there could be an alternative version of this definition that would be different if the different folds had different sizes. So because notice that, so here I just add all the errors and then I divide by k. But if folds have different sizes, it means that errors from a smaller fold, they have the same effect as errors from the bigger fold. So I'm not sure if this is okay. I just took this from the textbook, so I think it is used in practice, but an alternative would be to adjust it for the size of each fold. But I guess it's not done, so we are going to just adopt this definition. Okay, now here is an example, right? So if our full data, so I just took some 12 observations in the auto data set, but so suppose that this is just our full data. We don't have anything else, right? So then we're going to assign these fold numbers randomly. So in particular, observations 1, 4, and 9, together they are in the first fold, right? So observations 2, 7, and 10, so they are in the second fold, and so on. So there are 4 folds. So now we're going to train 4 models. Since we have 4 folds, we're going to train 4 models. So the first of these models is applied on observations on the set with observations 1, 4, and 9 being removed, right? So in order to train this model, we use observations 2, 3, not 4. 4 is removed, so 5, 6, 7, 8, 9 is removed, so 10, 11, and 12. So there are 9 of them. So we used 9 observations to train it, and we used observations 1, 4, and 9. So we applied this model to observations 1, 4, and 9 to find this mean squared error. So this is the mean squared error of this model on the observations 1, 4, and 9. And then so on, right? So if you look at fault number 2, then we removed observations 2, 7, and 10. So we trained our second degree polynomial on the remaining observations and applied it to these observations 2, 7, and 10 and computed this mean squared error. So this is how it works. Now, I have done a little experiment with the auto dataset again, so I just tried to reproduce whatever is in the textbook in Introduction to Statistical Learning. So they also do this with this auto dataset. So what I did, I basically tried cross-validation, k-fold cross-validation with k equals 2, 5, and 10. So notice that if k is 2, this is almost the same as this our initial validation set approach, because if k is 2, it means that we split our data set into two folds, right? But then it's just that in our initial validation set approach, we just train our model on one half and apply it to the other half. In the k-fold cross-validation, we do it twice, and then we train it on the other half and apply it to the first half and take the average error. But so which is why it kind of reduces the variance. So k equals 2 is better than just the pure validation set approach, so it has lower variance. But still, what I tried to see is how the variance in the estimated error changes when we increase the number of faults. Well, to be honest, this similar figure from the same experiment in the textbook, it looks more perfect. So they have lower variance. So it does look like my figure, but it is just that their curves are kind of closer to each other. They have less variance. So, but maybe it just happens. So I honestly tried to reproduce their experiment, and more or less, yeah, I saw that the higher is the number of faults, the lower is the variance, and it is already pretty decent, but still, may not be enough to really pick the best value of the degree. So, although it does seem that usually degree 7 works best here, I guess. So even in one experiment when 7 was not the lowest, it was almost the lowest, like it was 2 or 7. Well, in any case, so these are the results. Now, there is just one experiment from Introduction to Statistical Learning that I did not reproduce. I was too lazy, sorry about this. So, so I just inserted the figure from the textbook from page 182. So I hope you will excuse me for this, but yeah, it was just too much. So this is the most difficult of them, and I hope it doesn't matter much. The purpose of this experiment is to show that the true mean squared error for the test set. So the true test error. So this is the true test error. And the other two curves are the estimated error, either from leave one out cross-validation or from the tenfold cross-validation. So what we see here is that this leave one out cross-validation and tenfold cross-validation are actually very close to each other. So they almost follow the same trajectory. So which tells us that given that leave one out cross-validation is very, very computationally intensive, it doesn't really make sense to implement it. So we just do tenfold cross-validation, and that's it. So the other thing that we see here is that usually this tenfold cross-validation is a pretty good estimate to the true test error. Sometimes it is a bit underestimate, sometimes it is a bit overestimate, but overall it's okay, right? So here it's just okay all the way. So here it is okay on this for this range of degrees. Yeah, so flexibility here means the degree. Well, they're not using polynomial regression, so they are using something that is called splines, which we did not see here in class, but it is very similar. For the degree, it's going to be the same, so don't worry about it. So only in one of these two plots, the cross-validation error is kind of underestimates the true the true error, so which probably tells us that, yeah, sometimes this method is not perfect, but this is usually the best that we can do given our limited data. So that's the end of part 4 of the lecture, so please do the quiz.